All right, good day, everyone. We're going to continue on with our log formulas and log equations, things like that. Today, we're going to learn a lot more about how to use certain equations, formulas, things like that, and even our log properties to actually simplify, solve, expand, condense, do all those type of problems. Okay. Hopefully, today is kind of a big review over Algebra 2. That's one of the key things to understand is that a lot of this stuff was covered in the Algebra 2 section. We're just kind of going to go over it before we go into full solving because we need this information to actually solve out log problems. Okay. Throughout the process, I'm going to teach you a lot of different things. Make sure if you are taking notes, you get these down because these are all going to be important formulas. We'll also be taking these down in class tomorrow. Okay. But without further ado, let's go ahead and start talking about this. So basically, the first formula we're going to talk about is the log change of base. Okay. And the change of base formula is basically a way that we can actually solve out log with one without like using a graphing calculator, but two, it's a way that we've been doing it for a while to actually solve out log without a base of 10. Okay. To kind of give you a quick clarification, a couple things that you can actually do. If you have a calculator like so, okay. Okay. And on this calculator, we only really have a log with just a regular base. Okay. We don't really have a log base of 2 or like a base of 5 as we see here. So currently right now, there's really no way to solve it. Now, in your calculator, there are some options. Okay. If you ended up going to alpha window, okay, show this once more, alpha window, you actually do have a log base button in your calculator that will solve a lot of these out. So for example, I could do log base 5 answer of 10, okay? And it will work to solve this out. Now that's only if you have a certain type of graphing calculator that actually has this function. Most of the time we have to use something else or what we call a change of base formula. Now the change of base formula, simply put, is fairly easy to solve, okay? So we have the change of base, okay? Anytime I'm given a log with a different base than 10, what I'm going to do is basically try to create an equation with a log base of 10, okay? So notice how over here we took the log base 5 of 28, and we put the larger, the outside number on top, and the base goes on bottom. So if I have log base b of x, if I'm going to use the change of base, I'm going to write log of x on top, log of the b on bottom. Okay. So for example, in letter A, when I ask for log base 5 of 8, now I could plug that in the calculator with that method I showed you in a second ago, or I could just change this into log of 8 divided by log, oops, sorry about that, log of 5. And by doing that and simplifying it, I could actually get an answer of about 1.292. Okay. Now, they also can ask for this idea of log base 2 of 12 with base of e. Okay. The other idea that we have to understand is that base of e, that inverse of that function is a natural log. So while this log here is considered to have a base of 10, and that's a lot of reasons why we don't write it, if I want to try to find a base of e, I'm going to use a separate version of the change of base formula. Really, it's no different. The only thing that really changes is what value of log we actually plug in. In this case, we're going to use the natural log. So if I had the natural log of this value, it's going to become ln with the base b of x is going to become, I would write this out as ln of x over ln of the base. So really, if I want to change this formula into a natural log formula, it's not going to change any difference. You're still going to get the same answer whether you use the natural log or the log. In this case, if I wanted to work that out, this would come out to be natural log of 12 over the natural log of 2, which would give me an answer of 3.585. Okay. Now, no, this is a method of solving logs without like a graphing calculator. Now, like I talked about, like pretty much at any point, you could use this method of plugging it in. Okay. Oops, wrong one. You could always use this method of actually solving it out. For example, like if you have a graph calculator that uses this is a nice option. Base 5 of 8. Oops. This will always get you the answer as well. You know what I mean? But the thing is that in a lot of cases, let's say you don't have a graphing calculator. Okay, like SAT, they only give you a scientific calculator. You don't have this option. Okay, so what we want to do is try to figure out other ways to do this. Well, the other way to actually solve these out is using the change of base formula. Okay, log of 8 divided by log of 5. So all we have to do is change the base to put it on bottom and the value, put it on top. Okay. Now, that was the first formula we're going to talk about. The second ones we're going to actually start to discuss are the properties. And the properties kind of have a list of a couple of different ones. And a lot of times, these are ones that usually get the most confusing, and a lot of people forget kind of how to do it. But understand that it kind of goes hand in hand with operations. Okay, for example, when I look at the first the first property, we have product of a power. Okay, if I'm looking at my log version of it, multiplication, if I have a log that's being multiplied, or two values being multiplied inside of a log, I can split it up using addition. Okay, so really in this case, multiplication goes to addition. On top of that, if you ever try to think of like the opposite of an exponent, the same thing would be applied. If I had two values or two exponents being multiplied together with the same base, all I would do would be add together the exponents. Okay, so notice how these two kind of have relationships. Your exponents and your logs are going to relate back to each other. And the same things you used to do with the exponents, you are going to do with the log right now as well. The other one right here, if we have a division problem, so if we have division inside of a log, we're going to split that up using subtraction. Okay. And then the last real big one, the one that's actually I think is a property, is anytime you have an exponent, you're going to write it out in front of the log itself, okay, because it is a multiplier of that value. Okay. And then this last one's pretty straightforward. Basically, for this last one, a one-to-one. Honestly, personally, I know it's considered a property, but it's pretty straightforward compared to the others. Basically, if you look at this and you said if you had a log base B and a log base B here, that since they both have the same base, that M and N have to be equal to one another. And personally, I think that's kind of an easier one to look at because it's straightforward. If you took away the logs, all you'd have left would be M equals N. Okay? So let's talk about how to actually expand and condense these, because that's kind of the next important part. Okay? Oh, and before I do that, just real quick so you can glance at it. All right, for all these ones here, if I want to deal with natural logs, it's really no different. So if I had the natural log of M times N, this would come out to be the natural log of M plus the natural log of N. Okay, multiplication goes to addition. So really with this chart here, there's no difference of how we're actually solving it out. Okay, a natural log and a log are going to repeat the same thing. Okay, our properties don't change just because we're using a natural log. Okay, same thing here. This is the last one I'll write out. If we have the natural log base B of M to the power of N, that N value would come out in front and it'd be written as so. Okay, so really for this chart here, natural log isn't going to change my properties. Okay, all it changes is the fact that I'm using a different log value. Okay, instead of using a basic log, I'm going to use a natural log in that function. But let's go ahead and start talking about how do we actually expand and condense these. Okay, so if I look at these, try these B, what they want me to do is expand this expression. So basically, I got to take this log 5x y to the third and expand it out. Well, really, all I want to do is try to think about my properties. Okay, when I first look at this first one, I get an idea, and I'm basically saying, well, 5x and y are all being multiplied by one another, right? This is 5 times x times y cubed. Okay, so I want to think, okay, what can I turn multiplication into? Well, I can split these three up into an addition problem. That basically means I can change this into log of 5 plus log of x plus log y cubed. Notice how each and every one get their own value of log, and because they were all multiplying, all I had to do was split them up into three separate addition values. Okay? Now, for the last step, and let's just pretend like this isn't here. For the last step, I want to take this 3 and bring it to the outside. Okay? That value pretty much needs to be out in front. Anytime you have an exponent and you're trying to expand, we can bring that value in front to get to a final answer of log 5 plus log x, and then plus 3 log of y. And I've expanded that log out to get to my final answer, which is this. Okay? And that's really all we're doing for those log properties. When I'm expanding, all I really want to do is try to expand it out to the point where I use my properties, where multiplication goes to division, division goes to subtraction, and then I take exponents out in front to where each and every value gets its own log. Okay? A lot of times we do this when we're actually going to start solving, because I can't really solve this with all the unknowns involved in here. But I might have a chance to actually simplify and solve it when I get down to this point, because everything is separate. Okay? The last one we're going to talk about is a condensing problem. Okay? Where what I'm really going to do is condense these values together basically by working in the opposite direction. Okay? Addition goes to multiplication, subtraction goes to division, and so forth. Okay? So here's how I'm going to look at this first problem here. Letter A. We have 3 ln of x minus 1 minus ln of x. Well, I want to first take the idea of, if I have a value out in front, that's got to be an exponent. So I want to bring that exponent back in. That means I can write this as the natural log of x minus 1 cubed, because it becomes the exponent, minus ln of x. Well, my last step now is I got to try to think which property is going to simplify a subtraction. Well, if I have a subtraction in my logs, I can change this into a division problem, in which the original value is going to become the top, or the numerator, while the other value is going to become the denominator. So my final answer comes out to be the natural log of x minus 1 cubed divided by x. Okay? Now, we'll be going over a lot of these in class tomorrow, just to kind of help solidify our knowledge on it. These do get to become more complex, but the thing is that if you're always following your properties, in the end, it should always fall in line, okay? The nice thing about them is that you're not really solving anything yet. You're not working anything out. You're not trying to get to a certain location. All you're really doing right now is just moving values around, okay? And we do this by using our properties, which are shown on the other page, okay? We'll go over the rest of this in class tomorrow. Kind of wanted to give you a short video for today. Besides that, have a great day.